Okay, so Newton's first law, one of the big ones, that's that objects at rest will stay at rest and objects in motion will stay in constant motion unless they are acted upon by some unbalanced force. Let's break this down step by step, because even though there's a lot in that, we can unpack this and make it so that it's actually usable and helpful for us in various situations. So an object at rest. We know at rest just means that something isn't moving, right? Its speed is 0 meters per second, miles per hour, whatever your personal favorite unit for speed is, but it's not moving, right? And in this simulation that we used in class to the right, we have this box. It's sitting still. We can see that. The simulation doesn't show any forces acting on this object because the simulation is really only focused on what this little mannequin person is doing to the box. But we know that as long as this object is somewhere near a planet or some large mass, we should include the force of gravity here. So we'll assume that it's on Earth. But the reason that this object isn't moving, and I want to take this back for a second, we know that since this object is at rest and stably at rest, the forces acting on this crate must be balanced. And right now, if I left this as my free body diagram, just the force of gravity, this is not a balanced force. For there to be a balanced force, we would need just as much force pushing this object up as there is pulling it down by the force of gravity. So in this case, what's causing this to be balanced is going to be a normal force. And if we remember from other videos or from class, a normal force is some force exerted by some stable surface perpendicular from its surface, or basically straight out from a surface. So that's exerted by the ground, by tables, desks, chairs, and in this case it looks like a little sort of like skateboard that's sort of holding this thing up, or a little crate holding this thing up. Now, since these are the only two forces acting, we can also say that these forces should probably definitely be equal to each other. There is an important difference between balanced and equal forces. There are times when forces would be balanced but not equal. There are times when forces would be equal but not balanced. You can see another video, or you can play around with that and figure that out on your own, but that's in a different video if you feel unsure about that. But in this case, these forces are equal. The forces are balanced, which is why this object that's at rest is going to stay at rest. Now for the second part of this, objects in motion will stay in constant motion. Let's see that here in this familiar situation. So if we exert a force pushing this to the right, we can see while we're exerting this force, the object is speeding up. But once we stop exerting that force, now there's no applied force anymore by this little mannequin person, but the object is still in motion. And this is actually still the free body diagram that represents the forces that are still acting on this object. Its mass didn't change, probably, so the force of gravity didn't change. And if the force of gravity didn't change, this normal force could not have changed either. They're still equal and opposite, balancing out. So this idea of objects in motion staying in constant motion reinforces the idea that objects don't need forces to stay in motion. Actually, we would need a force to stop this object from continuing to move. And we can show that if this person starts to exert this backwards force on our object. I almost brought it to rest, but we would need that to happen in order to make it stop moving. But if we just want this box to keep moving to the right at the same speed, same velocity, then we just need to take our hands off and let it work and let it keep going forever and ever. And we could leave this going for hours, and it would just keep staying like that. Now, one way that we see this written about in problems is you'll see this sort of key phrase that should clue you in, and that's constant motion is sometimes referred to, and actually more commonly referred to, as constant velocity. Right, so velocity is a description of an object's motion, including both speed, that's just how fast, so in this case it's 20.8 meters per second would be the speed, but the velocity also includes direction. So the velocity, what it looks like to me is it's 20.8 meters per second to the right. So it's a full description of how an object is moving in this instant, including both how fast, the speed, and the direction that it's moving in. Now, In class, we've seen some slightly more complicated examples of this too. So if we have an object, even with horizontal forces acting on it, so if I exert some force on this object, let's get our values of everything going here. So we have a 94 Newton force acting here. And if these two forces that are acting on this object are equal, so if we have a 94 Newton friction force, and I'll add this to our free body diagram over here, we have a force of friction that is equal to this applied force going to the right. So I put 2 tick marks there again because these forces are equal to each other, but not necessarily equal to our gravity and normal forces. But notice that for this object in motion, it will stay in constant motion as long as these forces are acting, because these forces are all still balanced. So an important thing for us to remember is that we could have forces, we could even have a person pushing this object, but if there's some force working against this, or if instead of there being friction, if there were another person for whatever reason pushing the opposite direction, we could still have that object moving with its constant velocity or with constant motion because those forces are still balanced. So an important, very applicable way that we've used Newton's first law is if you're told that an object is at rest or is like stably at rest, or that it moves with constant velocity, the forces acting on it need to be balanced. And that's a very useful thing to remember that we've seen a lot of times in class and will definitely come up in the future throughout our work this year. Now, some of the other sort of implications of this, of Newton's first law, is like for how long contact forces act, right? So our first unit was all about gravity, electrostatic forces are non-contact forces, but now we've been thinking about like, well, a contact force is like what this mannequin is doing to the box, right? We can see them, or at least it seems to us, like it looks like they are touching. Now, for this projectile, we investigated what it really means for contact forces to act and how long they actually act for. So if I launch this cannonball out of this cannon, and I'll turn on slow motion so we can see this, you'll notice that once we launch this, the only force that still acts is this downwards force of gravity pulling this cannonball and sort of bending its motion back down to the ground. Once it leaves the cannon is no longer exerting this force upwards, or once the explosion has no longer, or has done its force, has exerted its force upwards to put this cannonball in motion, this cannonball is no longer experiencing that force. It was affected by that force initially, but now the explosion, the explosive gases, the cannon is not touching the cannonball, so the only thing that still acts on it is this force of gravity. So that was another sort of key idea, was like how long do contact forces act, and it's really only as long as the object is in contact with whatever is exerting that contact force. Now, for the object at rest, we investigated that with this other spring simulation, and the only difference here is that instead of there being a gravity and normal force, now it was gravity acting to pull this mass downwards, but it was a spring force that was keeping this object hanging in the air and stably at rest in the middle of the air with the ground, however far below it. So Newton's first law is very applicable. It's not always obvious when it becomes important, but it is always true that objects at rest and objects in motion will stay in their current state unless we have some kind of unbalanced force, like if I strengthened this person's force, now we can see this object speeding up. But this is always going to be true, and one of the keys is knowing that sort of key phrase, constant velocity, means that these forces must be balanced, and then figuring out how we can make that true in our free body diagrams and how we can solve that problem knowing this.